Hello, welcome to my talk on derivations of Bernoulli's equation. We will see there are quite different ways to derive Bernoulli's equation. This is the first part for deriving Bernoulli's equation based on the direct physics. So in this talk, we will first talk about what is the Bernoulli's equation and why it is so important. Then a brief history of Bernoulli's principle and equations will be introduced. And then we will discuss the assumptions for Bernoulli's equation. Then we will see the streamlines and the stream tube of the fluid, which would be used for deriving Bernoulli's equation. And then the force analysis acting on the fluid segment. We will see a detailed calculation of the force acting on the fluid segment. Then the dynamics of the fluid segment, which would lead to the Bernoulli's equation. In the first slide, we will see what is the Bernoulli's equation and why the Bernoulli's equation is so important. Basically, Bernoulli's equation is an integral form of Euler equation for inviscid flows. And the Bernoulli's equation is a mathematical expression of the Bernoulli's principle, which was discovered by Daniel Bernoulli. The pressure decreases when the fluid velocity increases. Bernoulli's equation was formally first derived by Euler in 1752, but it is still titled as Bernoulli's equation. Bernoulli's equation is the most applied equation in fluid mechanics. For example, the pipe flow and the open channel flows, which would be very practical when with the modifications for the losses in the flow, as well as with pumps and turbines. Bernoulli's equation is used for pitcher tube and venturi tube, which are used for measuring fluid velocity and flow rate. And these tubes are still widely used in practice. Bernoulli's equation is very important for the fluids past the airfoil, hydrofoil airplanes in building the relation between the velocity and the pressure. And the Bernoulli's equation is also important for the wave structure interactions and many more. As we know, all fluids are viscous. However, the Bernoulli's equation is only for inviscid flow. Thus, we have a question: can the real fluids be taken as inviscid? To answer this question, we can see the list of the common fluids. Here we have air, water, milk, cream, oil, tomato juice, honey, mayonnaise, sour cream. And in this column, the fluid viscosity mu is given. So this is the typical definition to define the absolute viscosity effect for the fluid. If mu is large, that means the fluid would be more sticky. And if we look at the common fluids, air and water, their viscosities are quite small. And in fluid dynamics, we are more talking about the kinematic viscosity nu. It is defined as the viscosity divided by the density. So it is a relative viscosity, but it is an important factor in the fluid dynamics. So now, the kinematic viscosity, we can see the water has the lowest kinematic viscosity, so as the air. Here in this table, only milk has lower kinematic viscosity than the air. And we can see like honey, mayonnaise, and sour cream would have much larger, more than 2,000 times than water. So these are the very sticky fluids. Now, from this table, we can answer the question, can the real fluids be taken as inviscid flow? The answer is yes, because the most common fluids, the air and the water, both have very small viscosity, the kinematic viscosity. So in many applications, they can be taken as inviscid flow and the potential flow in many practical problems. This is why the Bernoulli's equation is so useful in many practical applications. Daniel Bernoulli was the first one who initialized the pressure-velocity relation in the fluid dynamics. In 1738, he published his book Hydrodynamica, in which the Bernoulli's principle was published. Pressure decreases when the fluid speed increases, and this is the plot he drew in his book. And his father, Johann Bernoulli, also studied the Bernoulli's principle. Both then studied the pressure-velocity relation for some simple 1D flows. But the generalized Bernoulli's equation was actually derived by Euler in 1752. See the next slide. In 1752, Leonhard Euler derived the generalized Bernoulli's equation, as we have seen in many textbooks, which is in a form given as this. This is the term calculated with the fluid velocity, this is the pressure, and this is the term due to the height in the fluid. And these three terms together would be a constant. Here C0 is an integral constant. It depends on different situations. The Bernoulli's equation also means the sum of these three terms is a constant along a streamline. Now we regard the Bernoulli's equation is an integral form of Euler equation. However, this might not be the case for the Euler who derived and published the Bernoulli's equation, as well as the Euler equation. However, the publishing date would be different. Bernoulli's equation first in 1752 and the Euler equation later in 1757. I tried to find how Euler derived the Bernoulli's equation, but unfortunately I can't find the information. So the derivation of Bernoulli's equation in this talk would be referred to some textbook. As in the most textbook, the generalized Bernoulli's equation is under the following assumptions. The first assumption is flow is inviscid. That is, there will be no viscous force within the fluid. The mathematical expression for this is the fluid viscosity mu is 0. The second assumption is the flow is steady. That is, in the Euler representation, the local velocity is independent of time. That is, the velocity at a given or fixed spatial location is a constant. The expression for the steady flow is given by the partial differentiation of the velocity vector v with regard to t is 0. However, for Bernoulli's equation, we might have some exception. One exception is for potential flows. The unsteady Bernoulli's equation is possible, such as those in the wave structure interactions based on the potential flow theory. The third assumption is the body force acting on the fluid must be conservative. The most applied body force in the fluid is the fluid gravitational force, which is a conservative force. That means the body force per mass is given as this, so the gradient of the function gz is given as this. Here we can see when we calculate the gradient of the function gz, it is calculated as this. Obviously, we can see gz is independent of x, so this term would be 0. And gz is independent of y, so this term would be 0 too. Thus, the only term left is this, so this will be calculated as this because of the gravitational acceleration g is a constant. The fourth assumption here is the fluid is incompressible. This is an assumption for the fluid of low speed. If the fluid is incompressible, that means the fluid density would be a constant. And we can also have an exception for this assumption, since in very high speed flows, such as the flows past the transonic and the supersonic airplanes, the Bernoulli's equation can be derived for compressible flows if the ideal gas equation can be used. We will see this in different talk, but here for the simplicity of the derivation of Bernoulli's equation, the density of the fluid is assumed as incompressible. And for the general Bernoulli's equation, it is assumed the Bernoulli's equation is valid along a streamline of the fluid. See here the streamline, and on the streamline everywhere the fluid velocity vector would be tangent to the line. Based on the streamline definition, we have the mathematical equation for the streamline equation, which is given as this. The velocity vector v corresponding the vector ds on the streamline is 0. This means the velocity vector and the segment vector ds are in same direction or the opposite direction. And this streamline equation can be expressed as this. And in this talk, this streamline equation will be used for deriving the Bernoulli's equation. However, we have also an exception for this assumption, because in the potential flows, Bernoulli's equation is satisfied in the entire fluid field. Thus, there's no limit on the streamlines. Now we look at the flow streamline in the steady inviscid flow. On the streamline, the velocity vector would be tangent to the line everywhere. See the velocity vectors. And if we have a bundle of the streamline, these streamlines could form a stream tube. See here. And on each section, the flow parameters would be uniform, similar to the flow in the pipe here. At the section A1, the fluid velocity and the fluid pressure at this section would be constant. And same for the flow parameters at section A2. Here, the fluid velocity and the pressure would be constant. but they might be different from the physical parameters at the section A1. Now we look at the stream tube, a segment delta S, see here. And if we enlarge the section, we have the drawing at this. And we can look at the physical parameters, represent the parameters for the flow of the fluid segment. In this talk, the fluid density would be a constant because we consider the incompressible flow. And on the fluid segment delta S, it has the angle of alpha, see here, to the horizontal plane. And at the inlet, the pressure is P, the fluid velocity is V, and the sectional area is A. And at the outlet, here, the pressure is P plus delta P. The velocity is V plus delta V, and the sectional area is A plus delta A. And the possible forces acting on the segment. At the end of the segment, A and A plus delta A, due to the pressure P at A and P delta P at A plus delta A. And on the surface of the segment, due to the average pressure P plus half delta P. And we may also have the fluid body force due to the fluid gravitational force delta W. And we can see the fluid gravitational force is always pointing down in the opposite direction with Z direction. Now we can analyze the forces acting on the segment. Since the fluid movement would be on the streamline direction, thus the force would be considered only on the motion direction of the fluid segment, that is, on the streamline. We should be noted here, for the steady flow, the streamline and the path line of the fluid would be coincident. In here, we consider the body force first for the segment, delta F1, due to the gravitational force, delta W. So the component on the streamline would be given as delta F1 calculated as minus delta W sine alpha. Minus here is because F1 is in the opposite direction of the streamline. Now we consider the gravitational force delta W would be calculated as G delta M. Delta M is the fluid mass of the segment. It is calculated as this. Here, rho is the fluid density, and the value in the brackets is the average sectional area, and delta S is the length of the segment. So put all this together, delta F1 is calculated as this. Here, we can also see delta S times sine alpha equaling to delta Z. See here. So delta F1 could be calculated as this. And by dropping the higher order term, delta A times delta Z, we would have the expression for delta F1 as this. It is proportional to delta Z. In here, we would like to look at the surface force due to the pressure acting on the sections of the segment. At section A, the pressure P, and at section A plus delta A, the pressure P plus delta P. But we should notice the direction of the pressure at both ends. Thus, the force at the segment would be given as delta F2 as PA minus P plus delta P times A plus delta A. That's because P is in the same direction as the streamline, and P delta P is in the opposite direction with the streamline. So we calculate this expression by dropping the higher order term delta P delta Z. So we have the expression for delta F2. Also, we need to consider the surface force due to the pressure acting on the surface of the segment. On the side of the surface, see here, the force delta F3 would be calculated as this. This pressure is the averaged pressure acting on the surface of the segment. This is the averaged pressure. And delta S is the length of the segment. Delta C is the arc of the small area. And the component on the streamline direction would be timing sine beta. Beta is the angle in here or here because of the increase of the area from A to A plus delta A. And consider sine beta times delta S would be equal to delta R. This is the radial increase of the section area from A to A plus delta A here. And we also consider the pressure is the average pressure, the constant, so we can move it out from the summation. So we have the expression as this. And we can see delta R times delta C is the small area, and the sigma of this value would be delta A. Therefore, delta F3 would be given as P delta A. Here again, the higher order term delta P times delta A is dropped. Now we come back to the steam tube. In a steady flow, we know the fluid local acceleration is zero. That means the partial differentiation of V with regard to T is zero. However, when the segment moves to a different position, its velocity could probably change in magnitude or in direction, or both. Thus, there will be an acceleration of the segment. So the motion of the segment would be on the streamline, since in the steady flow, the streamline is the same as the path line. So the motion of the fluid segment could be governed by the Newton's second law of motion given by this. Delta m is the mass of the segment, and the acceleration of the segment along the streamline would give as the normal differentiation of V with regard to time. And the force is the total force we considered, delta F1, delta F2, and delta F3. So these are the total force, including the body force and the surface force. So put all this force together, we have the dynamic equation for the segment given as this. Delta m equaling to rho A delta S. And these two terms cancel each other. So we have the expression as this. And remove A from each term. So the expression would be given as this. Here we change the derivative of V with regard to T to the derivative of delta S with regard to T. And consider a very short segment. So ds would be same as delta S, dz same as delta z, and also the expression delta S divided by dt would be same as ds over dt. It is the velocity v, and dp is the same as delta p. So the equation would be written as this in a differential form given as this. Here the expression would be equaling to v. And move these two terms from the right hand side to the left hand side. We have the expression as this. Obviously, this equation is integrable. Hence, we have the integral form of the equation given as this. Here, C0 is the integral constant. So this is the conventional Bernoulli's equation.